Okay, so we're going to discuss something called implicit differentiation, and that involves having some equation that has a mixture of x's and y's on both sides of the equal sign. And we would wonder how could we find a derivative of something like that. So we need a little bit of an explanation before we begin. The first is this. We ask, well, what is an implicit function in the first place? So we need to go back to what we've been doing. And what we've been doing so far is that we've been dealing with functions that have been defined explicitly. When we say an explicitly written function, what we mean is that we have y already expressed as some function of x here. So what we're looking for when we say explicit function, well, y is completely in terms of x. All of the x terms can be separated to one side of the equation. Y can be separated completely to the other side of the equation. So we call this an explicitly written function. We know how the derivative of this kind of thing works. We would be saying, well, dy dx, the derivative of y with respect to x, is equal to the derivative of each of these separate terms, right? So we would be taking the derivative with respect to x of 2x squared minus the derivative with respect to x of 3x plus the derivative with respect to x of 7. And as we know, what happens to each of those terms that contain x in them, well, when we take the derivative, we don't use this d dx anymore. We just wind up with an expression that looks like the derivative of y with respect to x, and that will be equal to 2 times the derivative of x squared. And that becomes, 4x. And we'll be subtracting 3 times the derivative of x with respect to x, and that's just 1, so it's 3 times 1, and then plus 0 over here, so we leave it that way, and our derivatives are written this way. So the question for us is, well, how do we determine what we mean by an implicit function? Well, here's a couple of examples of implicitly expressed functions. In each case, y is not written directly in terms of x, right? Our goal right here would be to find a derivative, if we can somehow find dy dx out of all this, and we need a little bit of a different method for doing this. Now, in this case, actually, we can express this circle with a radius of 4, x squared plus y squared equals 16, we could find a derivative if we wanted to by splitting it up, right? We know that we could isolate y squared to one side here, and we could say, well, y squared is equal to this 16 minus x squared, and then we could write it explicitly as two separate functions. We have a function y equals the positive square root of 16 minus x squared, which is this upper half of the circle, if we wanted to think of it that way. But we could also say that y was equal to the negative root of 16 minus x squared, and then we could go through and try and find the derivative of it that way. We would probably end up using that chain rule in order to do this and find our expression. So it is possible with some functions that are written explicitly just to rewrite them as explicit functions and try and figure it out that way. But I would defy any one of you to try and do it with this next one right here. This is called a Folium of Descartes, which is sort of an interesting shape. It curves around and then it goes off towards infinity to the right and kind of curves around, goes off to negative infinity off to the left, and this is just a section of the curve where it does something really neat. It's called a folium because it looks a little bit like a leaf. This is called the Folium of Descartes, and we might ask, well, what what could we do to find the derivative of that if we can't split it up? So that's what we're going to do.